Hello everyone, my name is Muhammad Al-Takruri. I am based here in University of Technology in Malaysia, in particular in their electric vehicle laboratory. Today I want to talk about our future in transportation or our research that might contribute to our future in transportation. The research titled A Comparison Study of Hybrid Energy Storage System Topologies for Electric Vehicles. As I know, you know, and everybody knows that electric vehicles have been gaining foot in the market. I'm not talking about trains or metro that use electricity as their main fuel. I'm talking about these B-segment vehicles that commercialized for everyday people use. The thing about these vehicles that they use these batteries, which are mainly and most likely are lithium-ion batteries. These batteries are delicate. I mean by delicate that they have limited life cycles, and these life cycles can be even affected by discharge rate, depth of discharge, temperature, or even the load fluctuations. Okay, so researchers have been trying to minimize the problems of the lithium-ion batteries. One of these solutions is to couple it with a supercapacitor. This supercapacitor has somewhat similar characteristics to the electrolyte capacitors. But one more good thing, why it's called supercapacitor, it has higher specific energy. It can store more energy, but still less than the lithium-ion battery. So it doesn't make it cannot handle all the energy requirement of a vehicle by itself. So the researchers coupled these together to complement the negatives of the lithium-ion battery, because the supercapacitor can have large specific power, can supply fluctuating loads without losing its life cycles, and its life cycles is much higher of that of the lithium-ion battery. Okay, our next problem, how do we connect these two different energy storage devices together? Well, the most simplest way is to connect them passively in parallel, but we don't utilize the full capacity of a supercapacitor like this. So what we do is use something called hybrid energy storage system topologies. In these topologies, we use a converter between the storage devices to interface between them or to the DC bus. Let's look at these differences and how many topologies of these do we have. Okay, let's talk about the topologies. First, we have the one we already talked about, which is the passive. We have a battery supercapacitor connected in parallel. We don't need a controller or a control algorithm or a converter. So this passive topology is the least expensive and least complicated to implement. Let's look at the other topologies. We have topology B. Here we use a converter. We have a half-bridge bidirectional DC converter between the supercapacitor and battery. So the supercapacitor is interfaced to the DC bus. And we have its dual, where we swap a battery and supercapacitor. Now we have the battery is interfaced to the DC bus. And finally, we can just use two converters. So both of the energy storage devices are interfaced to the DC bus. Let's talk about the advantages and disadvantages. There are several researchers, or in the literature review, we can see many reviews about this. We talk about the full active. The full active is the least attractive to implement inside a commercial vehicle, commercial electric vehicle to be exact, because we have to buy two converters and we have to fit them inside the vehicle. So it is unlikely to use this for moving vehicles. So we have the other options, the passive we talked about. We have now the semi-active battery supercapacitor. This one, it has low reliability because we are concerned with if the converter have failed or its controller have failed, then we cannot continue the operation of the vehicle. Meanwhile, on the other hand, if we look at its dual semi-active supercapacitor battery, if the supercapacitor or the converter or the controller has failed, we can somehow isolate that failure and complete or continue the operation of the vehicle. In addition to that, we have the advantage of the supercapacitor in the topology B, that we can utilize its capacity down to 50% of its voltage. So we can vary its voltage with no problem because we have DC-DC converter between it and the DC bus. While on the topology C, the supercapacitor is directly connected to the motor controller, and we have a limited range to operate in that. Okay, so we are left with A, B, and C. Our research is based on internal combustion engine. This internal combustion engine has been or being currently converted into electric vehicle. It is based on it is Daisto Siron 2015 manual transmission, or in Malaysia it's called Perodua Maybig. As you can see, most of the conversion has been done. We have here the battery pack assembled with the BMS. We have the onboard charger and DC-DC converter for the small battery already being tested. And the motor itself is in the vehicle, and we have run tests on it. It works. We can see the motor here connected to the manual transmission via the adapter plate here. If you want to see more details about the conversion, I put some of it in the paper of how we size the battery pack. It's based on the distance. And other parameters is also there listed in a table. Now we know our system parameters. What is left is to develop the simulation profiles to know which hybrid energy storage system topology that perform the best for our application. So we developed 4 simulation profiles. The first one is battery only. The second one, we have a hybrid energy storage system passive topology. The third one is semi-active supercapacitor battery topology. And the last one is semi-active battery supercapacitor topology. So let's see together the results. Okay, let's talk about the simulation results. We have 4 systems, as I mentioned before. We must perform the simulation on this driving cycle, which is the new European driving cycle. And this is one of the systems. The other systems is we modify this. I just wanted to show that it is implemented in MATLAB Simulink. I believe this one is the semi-active supercapacitor battery topology. So let's look at the simulation results for the current. Okay, A is the battery-only system, B is the passive, C is the semi-active supercapacitor battery, and D is the battery supercapacitor. As we can anticipate that battery-only, it matches the demand current. The battery current is matching the demand current. As for B, since we don't have control over it and only the internal resistances of the energy devices controls that, we have a little bit of contribution of supercapacitor. C, we can see that our energy management strategy can decrease the current of the battery as expected. D, we can see something more interesting. As we mentioned before that the DC bus is directly connected to the supercapacitor, the battery has, or the energy management strategy has to keep in mind or keep the DC bus voltage within range of the controller. So we can see occasionally the battery is charging the supercapacitor to maintain that voltage. Okay, so let's look at the RMS, one of the important parameters that we know how does our hybrid energy storage system is performing. Okay, we can see the 4 systems here on the left, and we can see the worst performing, to our surprise, is the semi-active battery supercapacitor, where it increased the RMS value of the battery current more than the battery-only system. This can be explained or can be noticed here at this point. We can see sometimes the demand current is above or larger than the battery-only system. This is explained because we have the supercapacitor directly connected to the DC link, and when the voltage drops, the power stays constant and we have to supply more current. So that's why we can see it's the worst performing here. After that, we have the battery only, then passive, and the best performing is the semi-active supercapacitor battery. If we look at the peak value, we can see the worst performing is the battery only system. After that, we can see a similar performance for the battery supercapacitor and the passive, as we see here. And finally, the best performing in terms of current is semi-active supercapacitor battery. Let's look at the voltages. A is the vanilla or original benchmark performance, where we have the battery only. As you can see, this is the voltage. For B, where we have the supercapacitor and battery connected together, we see the voltage is more stable. For C, more or less, we can see when the supercapacitor is not active, we can see similar performance of battery only. But at this point here, and here, we see an improvement in the DC bus voltage. It's not the same case for D, where the DC bus voltage is varying much more than the other cases, because the DC bus voltage is actually the supercapacitor voltage. So from this, we can see it reflected on the DC bus voltage standard deviation. The passive system is best performing. After that, we have the semi-active supercapacitor battery, and after that is the battery only, and finally the worst performing is the battery supercapacitor topology, as we can see it visible from this graph. And it is using this equation, we can see its similar story. After we have done the simulation and before implementing the hybrid energy storage system inside the vehicle, first we do a small scale experiment to validate the simulation. We have here this DSpace interface inside our computer here, and inside the computer itself we have the DS1104 control board, this control board connected to its interface here. Of course, we have a supercapacitor. We made it from 20 cells of this specific cells. You can see it in the paper. We have a battery pack here. And of course, the D-space, after it takes the different current and voltage signals, it will give us the gate driver signals. And these gate drivers will run our IGBT legs to make the converters, the DC-DC converter, either for the semi-active supercapacitor battery or the battery supercapacitor topology. And finally, yeah, we have the motor load here that make or emulate our driving cycle. Okay, so we already ran this experiment and we have the results. Let's go and check these results together. Okay, let's look at the experimental result. We have already seen the experiment setup. If you're looking for more details, refer to the paper. For the experimental result, we chose, for convenience, a smaller portion of new European driving cycle. In a similar manner, let's look at the current first. In the same order of the systems, we have the battery-only system in A, B is the passive, C, semi-active supercapacitor battery, and D is the semi-active battery supercapacitor. We can see in B that the supercapacitor is contributing more to the demand current. This is explained because the equivalent series resistance of the battery and supercapacitor is different than the simulation. We cannot achieve that with in a smaller scale. So as a result, we can see the supercapacitor is contributing more with smaller equivalent series resistance. As for C and D, we can see clearly here in this small driving cycle, which with having higher acceleration rate, that the battery discharge rate is indeed limited at a certain level. In this case, it's around 0.5 ampere for both cases. However, in case D, we can see the battery is discharging more. This is explained same as the simulation because the DC bus had to be maintained in a certain voltage range. So let's look at the battery RMS value for all the systems. We can see the battery only in this case is performing worse than the semi-active battery supercapacitor. However, the battery supercapacitor topology is still performing the worst among the hybrid energy storage systems. Then we have the semi-active supercapacitor battery and passive in very close results. As for the peak value here, we can see clearly that the active, semi-active topologies with energy management strategy kept its promise by reducing the discharge rate, followed by the passive, and of course the battery only is the worst performing. What about the voltage? We can see here the voltages for the same sequence of systems. A, we have the passive. We can see a variation, large variation of the voltage in this case in the small scale. B, we have the passive with much more improved voltage profile. C is the semi-active supercapacitor battery. We can see the voltage is somewhat similar to the passive. And D is the worst performing among the hybrid energy storage system, where the DC bus is actually the orange here with large variation. This is reflected here in the standard deviation of DC bus voltage. Battery only is worse, as we can be obviously seen from the figure, followed by the battery supercapacitor, and then passive and supercapacitor battery are having somewhat similar results. This is also can be seen with the DC bus voltage variations. Okay, what's our conclusion of this simulation and experimental study? We have seen, although the passive hybrid energy storage system topology doesn't use a converter or energy management strategy, it has excellent performance in terms of voltage stability. And the second conclusion is the semi-active supercapacitor battery topology excels in reducing the battery current RMS value and the peak value, regardless of the size in the simulation and experiment. Thank you for listening. I hope this video made you interested in our research. If you want more details, you can look into our paper that has been submitted to IEEE Access.